In this lecture, we are going to talk about linear optimization problems. All right. Actually, we can use KKT conditions and the algorithms that we discussed before for convex optimizations, for linear optimization as well. But there are more efficient ways that leverage the linear structure of these problems. So after this lecture, first, I want you to be able to use the Simplex algorithm to solve a linear optimization problem. And then we also want to, I want you to know some examples of linear programming. All right, let's get started with a linear optimization problem with equality constraints. So minimizing a linear function C transpose X subject to A, which is a matrix multiplied by X, which is vector of variables, is equal to B, which is a vector of known values. And we usually assume that all of the variables should be greater than or equal to 0. All right. So if I want to show it for the scenario where I have x1 and x2 as the variables, and then C is going to be C1 and C2. So vector of variables x1, x2, vector of coefficients for the objective function C1 and C2. A is equal to A11, A12, A21, and A22. And B is equal to B1, B2. So this is the general problem. This is an example. All right. For our example, we are going to have minimizing. So C transpose is C1, C2 multiplied by X1, X2, which is C1, X1 plus C2, X2. X1 and X2 are our variables subject to A11, X1 plus A12, X2 is equal to B1, A21, X1 plus A22, X2 is equal to B2. And also X1 and X2 are positive. So if I want to draw this, I'm going to have X2 on this axis, X1 on this axis. First of all, we want both X1 and X2 to be positive. So our answer is either this side or this side. Also, we have to, I want to graphically show this constraint. So each of these represent a line. So let's say this one is A21 X1 plus A22 X2 is equal to B2. And this one is A11 X1 plus A12 X2 is equal to B1. All right. So our answer is going to be, now we have to show C1 X1 plus C2 X2 for different values. All right. What does that mean? This one is C1 X1 plus C2 X2 is equal to 0. Why? Because it passes the 0 and 0 point. And then we draw this for different lines. So the optimal point is where both of these constraints are satisfied. and also the values are positive. So this is going to be our optimal point. To be more specific, first, we check that they should be positive. Then we check that they should satisfy this constraint, then this constraint. So the intersection of these two constraints is where our optimal solution might be. And also, this is where our function c1x1 plus c2x2 is going to pass. So this is a very simple case, but I'm going to talk about a more generic scenario next. Before doing that, let's see what will happen if we have inequality linear constraints. Subject to a1x is equal to b1. a1 is a matrix, b1 is a vector. a2x is equal, a2x is less than or equal to b2, and x is positive. So the question is how to transform a linear optimization problem with inequality constraints to an equality constraint problem. All right. In order to answer this question, we are going to use slack variables. Slack variables are going to be added to each of these inequality constraints. Let's say you have inequality constraint h of x is less than or equal to 0. So it's a1 x1 plus a2 x2 less than or equal to 0. In order to make this an equality constraint, I'm going to define a slack variable. Let's say I call it xs. This is a positive value. So if you add this slack variable to the left side of this inequality, you can guarantee that you can transform it to an equality constraint. So a2 x2 plus 1 multiplied by xs is equal to 0. So this slack variable is a positive value that helps transforming this inequality constraint to an equality constraint. All right. So as you can see, the coefficient for this slack variable is 1. And if we have multiple of this, it's going to be 1 xs1, let's say a3x1 plus a4x2 plus 1 xs2 is equal to 0. So if we want to write this in a matrix format, how we are going to represent this is going to be a2 and then 1 0 0 0 0 1 0 0 0 0 0 1. And then we multiply this by this new vector of variables x, xs1, xs sub 2, xs sub m. Let's say we have m constraint. So now if I want to expand this, the first row of a2 and this 1 are going to be multiplied by this vector. So it will be a2, let's say row 1 of a2 multiplied by x plus xs1 is equal to 0. That's how we transform these inequality constraints to equality constraints. And if I want to write this entire thing in a compact form, we are going to have a1x is equal to b1, a2, and now we have a matrix block, identity matrix, multiplied by x, x slack, and this is going to be equal to b2. All right. Now we also want to merge these two together. In order to do that, we have to add slack variables here. But as we know, slack variables are not going to change our equality constraint. So it's 0 here. The coefficient for slack variables is equal to B1. If we want to merge all of this, we will have A x prime is equal to B, where A is defined as A1. This is a block matrix, a block of 0, A sub 2, identity matrix. X prime is X and X slack, and B is B1, B sub 2. The rest of the problem are as before. So our problem is going to be minimizing CT X, because X prime, the slacks don't appear in the objective function. Subject to Ax prime is equal to B, and X prime is greater than or equal to 0. So this is how we transform a linear optimization problem with inequality constraints to an equality constraint problem. The next question is, as you may have noticed, we deal with minimization. When we want to use simplex, we try to show the problem in terms of minimization problem. So if you are given maximizing C transpose X, where X are our variables, and we want to represent it in terms of a minimization problem, we simply multiply it by -1, and this is what we are going to have. So we simply could transform a maximization problem to a minimization problem. All right, so before starting the simplex solution algorithm, I want to talk about the base variables. So we define xb as the base variables which are non-zero. Let's say you have x1, x2, x3, x4, and x5 as your variables. Before starting the simplex algorithm, you should know how many of these are going to be non-zero. So we call, let's say these three are non-zero, so we call them base, and these are non-base. So non-base variables are 0. So x4 and x5 are equal to 0. But the question now is, how do we determine how many non-zero variables do we have? So, or what's the dimension of? What is the dimension of vector xb? All right. So let's do this more visually. Let's say we only have one constraint. And our constraint is a11 x1 plus a12 x2 plus x3 is equal to b1. So in this case, and this is x1, this is x2. So we already know that x1 and x2 are positive values. So your feasible region is in this area. And then I'm going to try to represent this line a11 x1 plus a12 x2, something like this. So this is going to be our ultimate feasible region. Now the question that we have here is, where is our optimal answer? Our optimal answer is going to be somewhere at the corner, either here or here. So there is a proof for this in the linear programming book. I'm going to provide a reference to that book if you want to see what's the theory behind that. Why the answer to linear programming is always happening at the corners. But if the answer happens here, x1 is going to be 0 and we already set x3 to be 0. So in this case, x1 is equal to x3 equal to 0, and x2 is non-zero. Similarly, we can show if we have two constraints, a11 x1 plus a12 x2 plus x3 is b1, and a21 x1 plus a22 x2 plus x4 is b2. In this scenario, x3 equal to x4 equal to 0, but because we have two lines, so these two lines are going to intersect somewhere here, where x1 is non-zero and x2 is non-zero. So just a simple observation, dimension of x sub b, or variables, number of variables that are non-zero, is equal to dimension of vector b. What was vector b? We had a prime x is a x prime is equal to b. So dimension of b, or number of constraints, represent the dimension of the base vector. So this is the first building block for the simplex algorithm. All right, I'm dividing the vector of variables. Let's say vector of variables is x transpose. This is all variables. I'm going to break it into two components, base and non-base. So this is base, this is non-base. So we also have to break the coefficients for these variables in the objective function. So we break C, or vector of coefficients, to CB transpose and C sub D transpose. We also break A, the matrix A, which is matrix of coefficients, to the coefficients for the base variables, coefficients for non-base variables. Given all these, we are going to transform our original problem. So here I assume if the problem was maximization, we already transformed it to minimization. If the problem had inequality constraint, we already transformed those inequality constraints into equality constraints. So it's going to be minimizing CB transpose XB plus CD transpose XD. Our variables are X sub B and X sub D, subject to vector matrix B multiplied by the base variables plus matrix D multiplied by the non-base variables equal to B. XB is greater than or equal to 0, XD greater than or equal to 0. So here, XBs are non-zero, or basic solutions, and XDs are 0, or non-basic solutions. So the next important step for simplex algorithm is to formulate the tableau. So for the tableau, what I'm going to do, I'm going to start from the constraints and try to create the tableau. So let's bring this constraint. I'm going to rewrite this constraint. So we have B, XB plus D, XD is equal to B. So I try to calculate the base variables. So we have B multiplied by XB is equal to B minus D multiplied by XD. Now I'm going to multiply both sides of this from left to B inverse. It's going to be B inverse B XB is equal to B inverse B minus D XD. Then these two, because this is B inverse B, is identity matrix. So XB is equal to B inverse B minus B inverse D XD. All right. So keep this in mind. Let's go back to the previous slide. Here, what was the objective function? C transpose XB plus CD transpose XD. So I'm going to rewrite the objective function CD transpose XB plus CD transpose XD. What I'm going to do, I'm going to insert the value of XB here. Correct. So we want everything to be in terms of the XD values, right? So it's going to be CB transpose B inverse B minus B inverse D XD plus CD transpose XD. If we simplify this further, we have CB transpose B inverse B plus, all right, here I'm going to factor X sub D here. So we have CD transpose from here, and we have these elements minus CB transpose B minus D multiplied by XD. All right. And what's going to happen for the constraint? So this is our objective function. What happens to the constraint? The constraint was BXB plus DXD equal to B. We multiply it by B inverse from left. So we have I multiplied by XB plus B inverse D XD is equal to B inverse B. And on the other hand, for the objective function, what we are going to do, again, we are going to bring X sub D to the left side and bring everything to the right side from this equation. So I'm going to represent it this way. CD transpose minus CD transpose B inverse D multiplied by X sub D is equal to f of X, which is our objective function, minus CB transpose B inverse D. So these two equations are the core equations to create the tableau. All right, what's tableau? I'm going to explain it in the next slide. So let's rewrite those equations. We want to talk about simplex solution algorithm. If we rewrite those two equations, one of them was related to the constraint, one of them objective function. For the constraint, we had I multiplied by XB plus B inverse D XD is equal to B inverse B. And for D, and for the objective function, we had CD transpose minus CB transpose B inverse D XD is equal to f of X minus CB transpose B inverse B. So as you can see, we have XB here, we have 0 XB here, plus we have XD here, we have XD here. So the standard tableau, which is the first step for the simplex algorithm, is defined as here. So assume that here you have x base and xd. So we have I comes from here. We have 0. 0 comes from here. We have b minus 1, b inverse d, b inverse d. Here we have this cd transpose minus cb transpose b inverse d. And at the other side, we have b minus b inverse b and minus cb transpose b inverse b. So we are going to explain the simplex algorithm to solve this tableau representation. Before doing that, let's go back again and see the steps to determine tableau. So you don't need to actually memorize tableau. You start from your problem here, minimizing CB transpose XB plus CD transpose XD, subject to BXB plus DXD is equal to B. So what will happen here? You start from this constraint. You start from the constraint, then you try to keep the base variables at left side and write it based on the non-basic variables. Then you're going to insert this in your objective function and try to write the objective function in terms of some constant terms plus some matrix multiplied by your a vector multiplied by your non-basic variables. And again, you are going to write the constraint in this form. Based on this, you can determine your tableau. What is tableau? Tableau shows this one called relative cost vector. Tableau is nothing but the coefficients of objective function and constraint after making some changes, some matrix multiplications, and multiply them by their inverse and so on. So here we have I, which is coefficients of xb. What I can do, this column, this part refers to xb or the base variables. This part refers to x sub d or non-basic variables, and this part refers to the right-hand side of these equations. So you simply can create the tableau for simplex algorithm. All right, how does simplex algorithm work? The way that simplex algorithm works, I talked about our optimal solution to be at one of these corners. So the optimal solution for linear optimization problem, let's say this is your feasible space. Your optimal solution is at one of these corners. And by going from one corner to the other one, you evaluate the value of your objective function and see which one is the optimal, which one is the minimum value. So basically the rotations in simplex algorithm are jumping from one corner of feasible space to the other corner. How do we do that? We exchange variables in xb with xd. So we change the location of variables for non-basic and basic variables to switch from one, to jump from one corner to the other. I'm going to write the tableau. This time I just want to explain it in a written way. So we have unity matrix for xb. We have 0 here. We have the coefficients of xd. We have the relative cost vector. We have the base vector. The base vector that refers to xb's. And we have minus f of x here. All right. So this part refers to base. This part refers to non-base variables. So in each iteration, in each rotation, we are going to find one of these basic variables and one of these non-basic variables and switch their location. So we basically bring one of the non-basic variables to the basic. That's how we go from one corner to the other corner. So for how long should we do that? As long as there is a negative value in the relative cost vector, our solution is suboptimal. So we should do that. We should do this process until all of the values here for the relative cost vector are positive. So we should carry out these rotations. So just a reminder, this is how our tableau looks like. We have identity matrix here. We have b minus 1d, or the coefficients for xd. We have the right-hand side, or the base values. We have 0 here. We have relative cost vector. This is called relative cost vector. And we have negative value of our objective function. So now we are going to have 2 steps to conduct this. Let's see what are those 2 steps. So this was our tableau, I0 for x base, for non-base, coefficients, relative cost vector, and we have the right-hand side values here, minus f of x, base vector. All right. First, we have to choose one of these these. One, choose an xd, which is a non-basic, for which the corresponding entry in the relative cost vector is negative. Actually, here, preferably, we use the most negative one. So what does that mean? If these values are minus 4, minus 2, 1, and 6, we are going to choose the xd, the non-basic variable that corresponds to minus 4. So this is the column that we are going to choose. Then, in the next step, choose the xb, or the basic variables, for which the entry in the base vector divided by corresponding coefficient of x sub d is greater than 0, but as small as possible. All right, now it gets a little more complicated. Let me expand it. So let's move this here. So let's say here for xd1, I have the coefficients to be 1, 4, and then we have the relative cost vector minus 4. And then at this side, for the base vectors, we have 2 and 6. All right. So we already know that it's xd1 that we want to swap. but we don't know which of these. Let's say we have 1, 0, 0, 1. So this is x base 1. This is x base 2. Yeah, let me rewrite this in the next page. So we have x base 1, x base 2, xd1, which is selected, xd2. All right, so we have 1, 0, 0, 1. For xd1, we said the coefficients are 1, 4, minus 4. 1, 4, minus 4. This one was minus 2. That's why this is not selected. We choose the most negative value. And here at this side, the values that we have are 2 and 6. 2 and 6. So what we were saying was dividing these values by the coefficient of the corresponding xd. 2 divided by 1 is 2. 6 divided by 4 is 1.5. Now we are going to choose among the positive values, we are going to choose the smallest value, which is going to be 1.5. So if this one was -2, then this was our only choice, to choose the 1.5. But now that both of them are positive, we are going to choose this one. This one helps us to determine which of the base values we are going to replace. The base value that it has a 1 coefficient here. So in the next step, what we are going to do, we are going to swap xd1 and xb2. This is how a non-basic variable enters the basic variables set. So this is the rotation process for simplex algorithm. I'm going to explain the rest of simplex algorithm and the step-by-step process in the next lecture following this lecture. So what we explained in this lecture was linear optimization problem. We said that generally we are interested in showing linear optimization problem in terms of C transpose X with X's as variables subject to AX is equal to B and X's are positive. But what will happen sometimes? We have maximization problems. So we transform them to minimization by multiplying by -1. Or sometimes we have minimizing C transpose X, A1X, B1, A2X, A2X less than or equal to B2, X's are positive. So in this scenario, we transform this into equality constraint by defining a set of slack variables. Then we have A1, A2, I, 0 multiplied by X, X slack equal to B1, B2, and X's are positive. X slacks are also positive. Then we talked about simplex algorithm and the rotations. The rotations are the steps that we do in simplex algorithm to determine the optimal solution. So moving from one corner to the other. In the next lecture, I'm going to talk about the more details of the simplex algorithm.